Hello, everyone. Thank you for coming to listen to us. My name is Nikolai. I'm from Saber Interactive, and today with Jordan Logan from AMD, I would like to tell you about the World War Z and its Vulkan port implementation. First of all, a few words about the title itself. World War Z is the latest game developed by Saber Interactive and released during this spring. It's a third-person shooter created to play cooperatively with friends. The main goal is to stay alive, destroying hordes of enemies and simultaneously performing various missions. Our game runs on a PC with a Vulkan and DirectX 11 backends and on consoles too. It supports rendering to the resolution up to 4K. Well, here's the main ideas of our rendering system. We are doing a full Z pre-pass. It helps us to eliminate the overdraw and further color pass, but also provide the opportunity to do some pre-shading tasks based on Z-pass data. To decrease the complexity of the color pass further, we prefer to store the filtered shadowing information from the first 4 dynamic lights to the separate render target. For the shading itself, we use the forward plus clustered approach. It means that the dynamic lights and reflection probes are being restored to the camera space voxel grid, which is being used by the forward shading loop. Our engine employs the GPU-driven visibility system. It does the frustum and the occlusion culling for the whole scene. Then the results are read back on the CPU side. This approach involves the 2 frames latency. This is a rather classical scheme when the game update thread running in parallel with the previous frame rendering. And the GPU is running slightly behind all of this. So here is the GPU diagram for the 1 frame. The parallel rectangles seem to be running simultaneously, and the data and the arrows means the data dependencies. Let's start. At the start of every frame, we need to do the Z-pass. We are rendering objects in front to back order to fully utilize the high-Z GPU culling. Besides of depths, we also store the wall space vertex normals. This pass is almost stateless. It means that it doesn't use any additional textures, unnecessary vertex streams, or constant buffers. It has been designed to be very fast on the both sides, on the CPU and the GPU. For the shadows, we use a rather usual percentage closer filtering solution with up to 12% disk samples rotated by a screen space 3x3 give a matrix. Afterwards, the depth of a blur with a kernel of the same size is applied to the whole mask. For directional lights, we use the parallel split scheme with up to 3 splits. Each split first rendered into the shadow map, then corresponding depth buffer region marked with a stencil, and after that, the shadow information projected to the screen space is stored to the one of the channels of this mask. We also need to store the splits into the separate fixed resolution atlas, which is later used by the transparent geometry. Now it is very important to care about the occlusion term to show the contacts between the different objects. For the large-scale, high-quality occlusion can be easily pre-computed to the light map, but the solution generally doesn't work for the dynamic objects, like characters. The screen space ambient occlusion helps us a bit, giving a small contact occlusion, but in our case, that was not enough. We want something like soft shadows from the indirect lighting. So for that, we use the so-called the capsule shadows, the set of capsules attached to each character skeleton. And after that, each capsule can cast the ambient occlusion and the directional occlusion. For the directional part, we use the dominant light direction from the light probes grid. This combined term then applied to the indirect lighting and the reflection of the further color pass. So we ended up with the main shading path. This is the most heavyweight part of our frame. Lots of texture, additional vertex streams, and the huge, very long shaders, all merged here. Besides of the HDR color output, we also output small G buffer data to use in the further passes. For example, it can be the velocity vectors mask, which is used by motion blur or TA clamping logic. So that was a short review of the Saber rendering tech. If you are interested, don't hesitate to ask me some additional questions. Also, you can check the presentations of my colleagues from the latest GDC, one about the zombie rendering technique and one about the light map technology. But now it's the best time to talk about the Vulkan port itself. So let's first ask ourselves, does it really care to write tons of boilerplate code, debug hundreds of issues and GPU crashes due to the wrong synchronization, memory access, or something like this? The experience of our studio said that yes, it does. With Vulkan, you can greatly reduce the amount of CPU workload and also makes your GPU run faster. The opportunity to manually batching, submitting rendering comments is a great way to utilize your hardware more. As a bonus, you get the responsibility that you need to care about your video memory allocations by yourself. It's like a double-ended sword, because on the one hand, a great chance to make a mistake, but on the other, you doesn't have any driver explicit control. So you can do what you want with your memory resources. For example, you can alias them with each other. It helps to greatly reduce the overall video memory consumption of the application, and also helps to do the cool features, for example, like dynamic resolution rendering. At the end, it works on different operation systems, Windows, Linux, Mac OS X, and also on different platforms like Google Stadia. So it's a good time to accept this challenge and push the limits of your game engine development further. One of the most brightest features of the World War Z is the ability to show thousands of zombies on the screen at the same time. It helps to immerse the player to the atmosphere of the zombie apocalypse. As a consequence, it turns out that you can easily get a situation when the three main frame passes, like depth, shadow, and color, have a huge number of draw calls. So the CPU preparation cost becomes bigger, and your GPU starts being idling while waiting for a new bunch of rendering comments. To do something with that and decrease the whole number of frame draw calls, we use the occlusion queries. We order our Z-pass in the front to back order and store the number of visible pixels during the Z-pass. After that, we are waiting for a fence on the CPU side to guarantee that the GPU results are ready. And after that, we use this information during color path submission to skip draw calls which are completely hidden. In our case, it's a rather effective solution because it can greatly reduce the number of draw calls. Anyway, if you want to use such approach, it is very important to notice that you need to execute some work on the GPU while you're waiting on a CPU for the Z-pass results. Otherwise, your GPU will be idling while CPU is waiting for results, preparing new rendering comments, and submit them. With in case of direct 3D11 backend, the draw call submission is being organized by a dedicated graphics driver thread. And by default, we don't know exactly when the submissions will be produced. So it's possible to get the GPU idle. To do something with this issue, we need to explicitly flush the common buffer queue 2 times, one after the Z-pass and one before we are waiting for occlusion query results. It gives a small but not negligible CPU overhead. Moreover, DirectDR11 deferred context model doesn't suit the hardware well. It means that you need to exactly load the resources into the physical memory at the time you submit your command lists. So it So it gets completely unrealistic for us to use this solution for the multi-threaded submission. But with the Vulkan, we've got an opposite solution situation, because it's a completely application responsibility to organize the common buffers recording and providing the synchronization for the common resources. So it's not necessary to know the exact resource address during the commons recording. All of these benefits give us a good way to distribute the job across the multiple threads. Now engine we prefer to create not so many additional render workers to avoid unnecessary resource contention between the threads. In fact, we use the simple rule. If we have more than 4 physical cores, we prefer to use 2 additional extra threads to provide the recording of the common buffers. Otherwise, we use only 1 for submission and for recording. And in fact, it is obvious that to use multiple threads in a part of the frame workflow where the number of the draw calls is really huge. So our main targets are Z-pre pass, the shadow map pass, especially the case when you want to draw a lot of splits for the directional light, and the main shading pass, which is the opaque objects, the transparent objects, and particles. It is also very important to submit enough work to hide the operation system scheduling latency. Small VKQ submit calls can complete faster than the operation system can complete another ones. In World War Z game, we prefer to do only 5 queue submissions with approximately 24 common buffers recorded per frame. We prefer to avoid the explicit fence synchronization, so we just double the amount of common buffers. Due to the fact that we need to wait for results of the GPU Z-pass, we can guarantee that the GPU can't fall behind significantly. To summarize, I can say that Vulkan gives a great opportunity for the CPU-bound application. Because of no driver-side validation, we can spend the time for the stuff that really matters. In our case, it can save up to 40% of CPU time. There are the numbers from the AMD Ryzen 7 family CPU. Okay, let's move forward. Now it's time to talk about the GPU performance. Now, if your CPU is fast enough, GPU idle will be smaller, and there is a possibility that you can become a GPU bound. So there are several ways to improve it. For example, you can try to utilize your GPU hardware better. In fact, the rasterization becomes a real bottleneck for the draw calls, which use a small or an empty shaders. Computational power of the GPU units stay unused. Luckily, Vulkan provides us a good option, the Sync Compute Queue, which can run compute shaders in parallel with the main rendering. To get the desired effect, it is better to run simultaneously with the passes which are mainly rasterized geometry without any extra arithmetic or memory access work. So in our engine, we do the SSAO, the capsule shadows, the screen space reflections, and the voxel grid rasterization in parallel with the shadow splits rendering. Suddenly, we don't have enough time to finish this feature, so in fact, the post-processing and the frame buffer rasterization are the good candidates to move to async 2. So you can prepare your Z-pass commands for the next frame as early as possible. It is also a very important feature to control the number of vector registers which is used by your shaders. In fact, the GPU could run several instances of shaders on one compute unit in case of small register and local data storage consumption. So every time one thread waits for data loaded from the memory, the GPU can run another thread to prevent idling. Color pass shaders in our engine are the most expensive because you need to use a lot of register space to fetch, blend material parameters, and also together with the calculation and reflection loops. We optimize the number of registers in our shaders in different ways. First of all, we apply the cross-lane wave intrinsics. So we accelerate our Froxel grid loops by moving some calculations to the scalar registers, which are common for the whole wavefront. I think Jordan should tell you more about this in his part. And if it's not possible, we try to pack our material data in several ways. For example, we can move the 2 single precision values to the 1 as a 16-bit halves. And after that, you can unpack them only by the moment you really need to use them. Also, we try to use the 64-bit arithmetics for our reflection bit mask because we store the 8 cube maps with the indices of the 8 bits to effectively processing it with using less number of registers. Here's the small example. First of all, we fetch the albedo into the 4 vector registers. After that, it is clear that because of albedo is typically in an 8-bit normalized format, we can easily store it with a less number of bits without any quality losses. So in GCN architecture, it needs to use just one instruction to store values into 1 and 2 to do the unpack. So it's almost 3. Being able to execute the shaders on multiple queues, our game gets a significant benefit. We don't use any slowness on any vendors, but also in a difficult case, we can speed up our GPU execution by 10%. It's actually when the shadow map pass is really huge. Also, the opportunity to use the wave intrinsic and reorganize the shader data flow significantly helps compiler to produce the better results by reducing number of registers and accelerating the execution speed of shaders for up to 20 or maybe 33% in some cases. Now let's talk about the memory management in Vulkan. Previous generation API managed memory automatically, but now it's a fully application responsibility to create resource, query its memory type, size, and alignment, allocate block of memory, and bind them together. In Saber, we prefer to use the Vulkan memory allocator from Adam Savitsky from AMD. It is well-documented open source library which was used in several AAA projects. It's continuously maintained and just working out of the box. It helps it greatly reduce the development time because you don't need to write tons of memory management code. Saber, we use the fixed number of random targets per frame. So it's obvious that some of them are used only during part of the frame. So we can easily save up some memory by aliasing resources which are not used at the same time. First, we collect some in-game statistics about targets' lifetime dependencies. After that, we mark each target with a special bit mask where collected information is stored. When our algorithm works like a simple CPU memory allocator, during the engine startup, you need to get all aliased resources for each random target. After you calculate the pool block memory layout respecting the dependency bits and alignment. After that, you can get its total size and allocate one device memory block. You can repeat this process for the other resources as well. So it's just a simple example for the 4 targets. Firstly, we allocate the largest target, with which is sharing memory with the 3 others. After that, we process the next, so its bit mask has the 0-bit being set, so we can simply reuse the same address as the first blue resource. With the next one, we have a small issue because we cannot share the space with a green target because they are used in a parallel. So we use the remaining space within the first blue resource. And after that, the last target, should be put it into the blue space, but actually we can't do it because the blue block is completely covered by another resources. So we just need to put it at the end of our common block, and after that we can calculate the total size and do the memory allocation. It is also very important to respect the alignment of the addresses of the render resources. In fact, it depends on how the resources laying down into the memory and from their swizzling, and also from the GPU access policy. So to keep in mind this issue, we remember these offsets as some kind of a fake render targets and track their maximum sizes. So every time we start searching the suitable space for a new target, we can easily understand are there any holes before. And if they are found, just start the search from the beginning of alignment hole to try to utilize it. So our Vulkan memory sub-allocation system mimics our console solution, so it helps to write the uniform code to maintain all of the platforms. It is simple because we exactly know when each target is used, so no explicit synchronization really required. And it's also greatly reduced the video memory consumption. In our test it saves more than 50%. One more important notice, if you actually want to share your compressed render targets with UFs, you actually need to do the explicit barrier with all the layout set to the undefined to reset the GPU driver metadata, because otherwise you can have a corruption, because driver thinks that the compression, the delta color compression is actually applied to the UF memory space. Well, having so low-level memory allocation management allows us to do a really cool features. For example, we can implement the dynamic resolution feature. We can simply allocate the memory for the largest version of the render target, and after that map the smaller virtual versions to the same memory address. After that, we can switch between them according to the frame workload. To get a workable solution, you need to use a prediction model to switch the resolution on time. To do this, first set the FPS goal target. After, you need to measure your frame statistics, the CPU and GPU timings. There are several ways to proceed with it, but we prefer to use an exponential smoothing average because it has a really fast response to the frame workload changes. To slightly smooth the results, we use the 2 frames history. Well, and here is the heuristic to choose the render target. So first, every frame the engine tries to determine is it GPU bound or not. And then it first checks if the average FPS is being lower than the target FPS, and if it does, we drop the resolution by 1 step. Also, if the GPU continues to be fully utilized, we drop another 5%. Otherwise, if the GPU starts being starving, we try to increase the frame resolution a bit. Our dynamic resolution system has been designed to keep in mind 2 points. Dropping resolution should work relatively fast, trying to fit the GPU to time targets as close as possible. Upscaling, the resolution should be applied with a certain pause. Only, for example, the last 20 frames, we had a stable GPU underutilization case. It helps to switch the resolution not so often and preserving the image details quality. Well, here is some kind of results of our dynamic resolution system. So first, for a certain amount of frames, we keep our system disabled. The engine uses the 100% of our GPU frame time and of the render target, and the GPU frame time is about 36 milliseconds, so it's completely unacceptable. But then we just switch on the system and the situation dramatically changed. The resolution percentage is now about 50%, but the GPU time is much lower, only about 16 milliseconds, which is enough to draw 60 frames per second. Okay, and at the end, I would like to mention the PCO management topic. We have a real problem with Vulkan that the VK create graphics pipeline functions works really slow and compare with analogous functionality in D3D backend. The cold boot of our game has taken up a very long time, up to 10 minutes. Spikes in creating shaders during game sessions was extremely large too. So to do something with this, we first of all split our shaders in a scene only and a full cache shaders. Scene only is the shaders which are used only by scene objects materials, and another full cache. They have we prepare their desks completely dynamically. So for scene shaders, we can compile only combinations which are really being used for the specific level, and for the full cache, we need to prepare all existing variants. The benefit of the scene shaders, we have an a priori knowledge about all of the settings, the render states, the render target formats, and so on. So we can easily gather and serialize this information for each scene and use it accordingly to create the PSLs during the level startup. One question remained: what to do with the full cache shaders? We can't recreate all of them because it's too long on memory space, ineffective. So at Saber, we use just a simple solution. We ask our QA team to play each level a few times and gather enabled in-game PSO statistics about the full cache shaders which is being used. Now we can reuse this information during the expert stage and pre-create the full cache dynamic PSOs, which is necessary. It just works in our case. So the number of PSO creations during game sessions are negligibly small. All of the steps helps us to reduce the number of to reduce the code level loading time dramatically from the 10 minutes up to 1.5. Of course, we need to use the internal Vulkan pipeline PSO cache because you can store the internal SA code and use it for the next time runs to create the shaders, to create the PSOs instantly. One important thing is to delete unused PSOs between the levels, because the driver has the limit for its own storage, and PSOs sometimes can migrate to the system RAM, which leads to the performance degradation. So that's it. Now it's time to to listen to Jordan about some optimizations.
Hello, I'm Jordan Logan. I'm the AMD dev tech that worked with Saber on World War Z. Now, if you don't know about what dev tech is, we provide direct support for the developers. We also help find optimizations and profiling, and if there's any driver issues, we'll work directly with the driver team to make sure that the game has the best experience. We'll also deal with any of those GPU-specific issues that are very hard to find and fix. So I'll talk about a few of the optimizations that I helped Saber with using Vulkan. The first thing is that the transfer queue. So Vulkan exposes the hardware DMA engines that are in most GPUs and lets you explicitly use them. In the older APIs, the driver would have to do some heroics to pull uploads and downloads out of the graphics queue into a transfer queue. So this helps on all platforms except APUs, and it's completely asynchronous to the graphics and compute resources on AMD hardware, and it is the fastest way to actually get data across the PCI Express bus. Caveats is that it has to be explicitly used, and you have to do all the synchronization yourself. Because of this, we recommend that you do not use the transfer queue for anything that would require the graphics queue to wait on it, because it takes quite a while to do that synchronization point. Because of this, the transfer queue is actually amazing at doing texture streaming, which we implemented into World War Z. And so in this case, while we're streaming on new textures, we can continue using the old texture. And once that texture is uploaded, we can just swap it out seamlessly because Saber used pre-baked descriptors. And so with this method, though, we did have to double the amount of descriptors since you cannot write to a descriptor that you are currently using. So there's 2 copies of every descriptor, and we just update the next frame's descriptor and then swap them out. Doing this, we are able to keep the texture stream completely asynchronous to the rest of the graphics, and so that this causes a much better experience to the players. There's no hitches from new textures coming in. So kind of a diagram of how this worked in Saber. A new texture request will come in, either requesting a higher MIP or a brand new texture. There's a dedicated thread that is just constantly spinning, waiting for work to come in. It'll read the texture and generate a transfer queue command list. It'll then submit this to a transfer queue, and then it'll wait for that to finish. Sometimes it can also be batching if there's a lot coming in at the same time. The transfer queue will then move the data across the PCI Express, and then we'll issue a barrier on the transfer queue to flush all the caches, and then it'll signal. After that, then the CPU thread can update the next frame's descriptor. There's quite a few gotchas with transfer queue. We ran into quite a few of these with World War Z. So first off, the transfer queue can actually have a completely different granularity than the other queues. So by Vulkan spec, it is required that you either have to do a full sub-resource copy, or have the number of pixels you're copying in your region has to be divisible by the queue granularity. So you have to query the transfer queue. And if you don't follow these rules, you can get a lot of undefined behavior. A commonly seen one is that the transfer queue will hang and never finish its command list, eventually causing a TDR. You also have to be careful, make sure you issue the proper barriers. If not, you could cause corruption, as some of the caches might have stale data because they weren't notified that there's new data in that cache line. One of the biggest optimizations that we did for World War Z involved the stencil mask. So World War Z uses a stencil mask to dissolve LODs. It does this using 4 draws, each one setting a different pixel inside a quad. And each of these draws has a different stencil ref and will reject a different pixel. I profiled this using the AMD profile, or RGP, short for Radon GPU profile, I saw that these 4 draws had extremely low visibility, occupancy, even though the shader doesn't do much. It was only using maybe 4 VGPRs and no LDS, so it should be running a lot faster. After digging in, I actually found out that these shader waves are so small that they'll actually finish before the GPU can watch another wave. But with Vulkan, we were able to actually optimize this quite well. There's a multi-vendor extension called Shader Stencil Export. This extension will allow you to export the stencil ref from inside the shader instead of through the render state. With this, we were able to take those 4 draws and combine them into a single one. And the shader ref export is exposed in both GLSO and HLSO. They have different names for it. GLSO calls it frag stencil ref, and it requires a GLSO extension. And HLSO calls it SV stencil ref. So with that, we combined those 4 draw calls into a single one, and this allowed us to get a 75% savings for this pass, since we were only issuing a quarter of the number of waves before. Another optimization that we did using Vulkan was subgroup operations that Nikolai mentioned earlier. These were introduced in Vulkan 1.1 and are supported by most desktop hardware, including AMD. This allowed us to bring over optimizations from the consoles that Saber has already done, as well as letting us do several new optimizations ourselves. You do need to query the driver to see which operations are supported in what stages and on what hardware, as it may vary between GPUs. So I'll go over 2 of the ones we did with subgroup ops. The first is that we used subgroup OR. So there is a whiting bit mask that is 32-bit wide that specifies on that pixel what whites it needs to check and possibly apply to the pixel. So before, the shader will just whoop through this and bit shifting it over again and again. So this meant that because of how GPUs work, and that means there are several lanes being disabled. So we were able to take this and actually use subgroup OR to scalarize these resources to try and reduce the VGPR pressure. So I have my imaginary GPU here that has 4 lanes and 4 bit masks. And you see here that the lane 1, 2, and 3 have some bits set. That'll be the green, and the rest are red. So what subgroup OR does is it takes every single lane and ORs it with the headers and broadcasts it to all of them. So it kind of looks like this. And then the compiler is smart enough to realize that this is now uniform, and so since it can now promote this to a scalar, which moves it out of a VGPR for AMD. The other one, a little bit more complicated, is that we use subgroup broadcast first to do a similar thing with cube map indexes. Except for these are not bitmaps and actual indexes, we can't use subgroup OR. We also used broadcast first in a lot of different places to help give the compiler a opportunity, well, a little hint that this is a uniform resource. So the way how broadcast first works is it will read the first active lane. In this case, it'll be lane 1, and moves that to a scalar. It then takes that. We then took that and we would compare it with the vector version of this to disable the lanes that are not active. From this, the compiler could figure out that everything in that if statement could be scalarized and was able to reduce the VGPR pressure. Then in the next loop, we would disable everything that actually had the value in that if statement, and then we would continue doing this to promote another scalar, and continue doing this until we're out of indexes. With these 2 optimizations, we were able to reduce the VGPR pressure in the lighting and was able to give a very large performance boost with no visual difference. So that's the end of my section. I'd like to give thanks to everyone that helped make this possible from AMD and Saber. Thank you, and we can answer any questions you have.